Pick up a rock. Hold it in your hand. Feel the weight of it. You think you're feeling mass. You think mass is the thing that makes the rock heavy. The matter compressed into that small volume. The atoms stacked together. The particles crammed inside. The density of existence itself. You think if you could count every atom, add them all up, you'd arrive at the mass. That mass is a quantity, a measurement of how much rock there is. This is the picture everyone carries. Mass as substance. Mass as the stuff that's there. It's wrong. When you hold that rock, you're not feeling how much is inside it. You're feeling the earth pulling on it. Gravity acting on mass, yes. But that pull doesn't tell you what mass is. It tells you what mass does in the presence of a gravitational field. So you think, fine, weight isn't mass. Weight is mass times gravity. Take away the earth, take away gravity entirely, and you'd have pure mass. But what would that be? You imagine the rock floating in deep space. No gravity, no weight, but still the same rock, still the same mass. You imagine that the amount of rock hasn't changed, and you'd be right that something hasn't changed. But it's not an amount, it's not a substance, it's not stuff. What hasn't changed is how hard that rock resists you when you try to move it. Push the rock in space, it pushes back. Not because it's heavy, it has no weight in space. It pushes back because it has mass. And mass, at its core, is resistance. Not resistance like friction. Not resistance like a barrier. Resistance to acceleration. Resistance to change in motion. The rock doesn't want to speed up. It doesn't want to slow down. It refuses in a very specific, measurable way. That refusal, that stubbornness, is what you've been calling mass your entire life. And here's where the discomfort begins. If mass is resistance, not substance, then where is it? What part of the rock resists? Is there a tiny resistor hiding in each atom? A little anchor holding motion back? No. There's nothing holding anything back. There's no substance of resistance. Mass isn't in the rock. Mass is what happens when you try to accelerate the rock. You think you're holding matter. You're holding a relationship, a dynamic, an interaction waiting to occur. And once you see this, you can't unsee it. Imagine you're an astronaut, floating in the International Space Station. Everything is weightless. You are weightless. A wrench floats past you. A laptop drifts by. You reach out and grab the wrench. It has no weight. It doesn't pull down on your hand. There is no down, no gravity acting on it in any meaningful way. But now you try to swing it. You pull your arm back and whip the wrench forward, and it resists. Not because it's heavy. It has no heaviness, but because it has mass. Your muscles have to work. The wrench fights your effort to accelerate it. And when you let go, it keeps drifting at constant velocity, because now you're not accelerating it anymore. No force, no acceleration. But the mass is still there, always there, waiting to resist the next push. Now imagine a massive steel beam, floating nearby, weightless, just like the wrench. You can nudge it with one finger, and it will drift away slowly, obeying Newton's first law. No force needed to keep it moving. But try to stop it. Try to accelerate it quickly. Try to shove it hard to the left. You can't. Your muscles aren't strong enough. The beam resists. Doesn't feel heavy. It feels stubborn, inertial. It refuses to change its motion quickly, and the refusal is proportional to its mass. This is what mass is. Not weight, not substance. Inertia. The measure of how much an object resists being accelerated. And here's the key insight Feynman wanted people to grasp. Mass only reveals itself through interaction. You cannot see mass. You cannot measure it by looking. You measure it by pushing, by accelerating, by applying force and observing resistance. Force equals mass, times acceleration. You learned that equation in school, but you probably thought of it as a formula for calculating force. It's not. It's a definition of mass. Rearrange it. Mass equals force divided by acceleration. You apply a known force. You measure how much the object accelerates. The ratio tells you the mass. Mass is the proportionality constant between force and acceleration. Nothing more, nothing less. It's not hiding inside the object. It's not a property the object possesses while sitting still. It's a relationship, a response. An object with large mass requires large force to achieve small acceleration. An object with small mass requires small force to achieve large acceleration. That's it. That's the entire definition. So when you hold that rock on Earth, you're feeling the Earth accelerated downward at 9.8 meters per second squared, and the rock's mass resisting that acceleration. The resistance creates a force. The force presses into your hand. You call it weight. But weight is just mass revealing itself in the presence of gravity. Take gravity away, and mass is still there. Silent, invisible, waiting for you to try to change its motion. And when you do, it fights back with perfect mathematical precision. You think you understand this now. You think inertia makes sense. Objects resist acceleration. Fine. But you still think the mass is in the object. You still think there's something inside the rock, inside the steel beam, inside the wrench that causes the resistance. There isn't. And that's where things get strange. You think mass comes from matter. And matter, you think, is made of atoms. Atoms packed together. Tiny spheres of substance stacked into solids, spread into liquids, dispersed into gases. You imagine an atom as a thing. A small, dense thing. A nucleus at the center, electrons buzzing around it. Tiny, yes, but real, solid at some level. This picture is wrong. An atom is not a thing. It's almost entirely nothing. The nucleus sits at the center, protons and neutrons clustered together. The electrons exist in a cloud around it. But that cloud isn't a surface. It's a probability distribution, a region where you might find an electron if you looked. And the space between the nucleus and the electron cloud. Empty. Not empty like a vacuum you could fill. Empty like there's nothing there. No substance, no matter, no stuff. The numbers make it worse. If you scaled a hydrogen atom up, so the nucleus was the size of a marble, the electron's orbital would extend about half a mile away. Everything in between? Nothing. The atom is 99.99% empty space. And that's not poetic language. That's measurement. So where's the mass? You think, fine, the mass is in the nucleus. That's where the protons and neutrons are. That's the dense part. That's the substance. But go deeper. Protons and neutrons are not fundamental. They're made of quarks, 3 quarks each, bound together by the strong nuclear force, mediated by particles called gluons. Quarks are point particles. They have no size, no volume, no spatial extent. You cannot measure the radius of a quark because it doesn't have one. Gluons, also point particles. No size. Electrons, also point particles. No size. You are made of particles with no volume. So where is the mass? If mass were substance, if it were stuff, then particles with no volume would have no mass. But they do. An electron has mass. A quark has mass. And when you bind quarks together into a proton, that proton has mass. But none of these particles are taking up space. None of them are little spheres of condensed matter. They are mathematical points, zero-dimensional. You might protest. They must have some size. We just can't measure it yet. No. Experiments have probed electrons down to scales smaller than 10 to the power of -18 meters. No structure, no radius. If electrons have size, it's smaller than anything we can currently detect, and theory suggests they don't have size at all. So the picture collapses. You are not made of tiny, solid things packed together. You are made of empty space with point-like particles embedded in it. And even those particles aren't located in the classical sense. They're excitations in quantum fields, or ripples, disturbances, patterns of energy with no spatial extent. And yet you have mass. The rock has mass. The wrench has mass. You have mass. But if you stripped away all the empty space, if you compressed a human body so that only the actual matter remained, you wouldn't have a smaller person. You'd have nothing. A collection of point particles with no volume. And those point particles would still have the same total mass, because mass is not volume. It's not density. It's not stuff packed into space. So what is it? You've been told atoms are the building blocks of matter. But atoms aren't blocks. They're not building anything. They're probability clouds around point-like excitations and fields. And the mass you feel, the resistance you experience, emerges from something else entirely. Not from the particles themselves, from the fields. There is a field that fills all of space. You are moving through it right now. You have been moving through it your entire life. It's not air. It's not gravity. It's not electromagnetic. It's the Higgs field. And every particle with mass has mass because it interacts with this field. This is not a metaphor. This is mechanism. Before the Higgs field was confirmed experimentally in 2012, physicists predicted it had to exist. Because without it, the equations didn't work. Fundamental particles, electrons, quarks, the building blocks of everything, should have been massless, moving at the speed of light, forever. But they're not. They have mass. They move slower than light. They resist acceleration. Why? Because they interact with the Higgs field. I think of it like this. A particle moving through empty space, truly empty space, no fields, would glide effortlessly. No resistance, no inertia. It would accelerate with infinite ease. But space isn't empty. The Higgs field permeates it. And certain particles couple to this field. They interact with it as they move. That interaction is resistance. The stronger a particle couples to the Higgs field, the more it resists acceleration, the more mass it has. An electron couples weakly. Small mass, a top quark couples strongly. Large mass, a photon doesn't couple at all. Zero mass. It moves at the speed of light because nothing resists it. Mass is not something particles have. Mass is something the Higgs field does to particles. You think you're starting to understand now? The Higgs field grants mass. Mystery solved. No, Sam. Mystery relocated. Because here's what they don't tell you. The Higgs field accounts for only about 1% of your mass. You weigh, let's say, 70 kilograms. The Higgs mechanism is responsible for less than 1 kilogram of that. The other 99%? It comes from somewhere else entirely. Protons and neutrons make up most of your body's mass. You learned this already. But a proton is made of 3 quarks, 2 up quarks and 1 down quark. The mass of an up quark, about 2.2 mega electron volts per c squared. The mass of a down quark, about 4.7 mega electron volts per c squared. Add them up. 2.2 plus 2.2 plus 4.7 equals 9.1 mega electron volts per c squared. The mass of a proton? 938 mega electron volts per c squared. The quarks account for less than 1% of the proton's mass. So where is the other 99%? It's not the Higgs field. The quarks already got their mass from the Higgs field. That's the 9.1 mega electron volts. The other 929 mega-electron volts, the vast majority of the proton's mass, comes from the energy of the strong force holding the quarks together. Energy, not particles, not substance. The gluons mediating the strong force. The quantum chromodynamic field, binding quarks into protons. The sheer violence of the forces inside the nucleus. That energy has mass, and you are made of it. The Higgs field is elegant. It's fundamental. It's the reason particles aren't massless. But it's not the reason you aren't massless. You are not made of Higgs-granted mass. You are made of bound energy. Feynman understood this deeply. He knew the Higgs mechanism, though it wasn't confirmed in his lifetime, would only answer part of the question. The other part? The binding energy? That's quantum chromodynamics. That's the strong force. That's one of the most complex, computationally intensive areas of physics, and it tells you something uncomfortable. Your mass is not a gift from a single field. It's an emergent property of violent, seething interactions happening inside every proton and neutron in your body. Mass is not given. It's generated. Constantly. From energy that never stops moving, Einstein told you E equals mc squared. You think it's a conversion formula. You think it means you can turn mass into energy, or energy into mass, like exchanging currency. That's not what it means. It means mass and energy are the same thing. Not equivalent. Not interchangeable. The same. Mass is energy. Energy is mass. They are two names for the same phenomenon, measured in different units. When you hold that rock, you are holding energy. Frozen, condensed, locked into a form that resists acceleration. But energy nonetheless. And here's the part that destroys your intuition completely. Most of the energy, most of the mass, inside you is not the mass of particles. It's the kinetic energy of quarks moving near the speed of light. It's the potential energy of the strong force field binding them together. It's the energy of gluons being exchanged, created, annihilated, created again in an endless quantum storm. Inside every proton in your body, 3 quarks are trapped. They cannot escape. And the strong force gets stronger with distance, pull quarks apart, and the force pulling them back intensifies. It's like a spring that never weakens. So the quarks move, frantically, relativistically, whipping around each other at substantial fractions of the speed of light, confined to a space smaller than 10 to the power of minus 15 meters. That motion is energy. The gluons holding them, those are energy. The field itself fluctuating, seething with virtual particles popping in and out of existence. That's energy. Add it all up and you get 938 mega-electron volts per c squared, the mass of the proton. But nothing in the proton is sitting still. Nothing is static. There is no substance at rest. The mass you measure, the resistance you feel, is the total energy of this contained chaos, divided by the speed of light squared. E equals mc squared rearranged is m equals E over c squared. Mass is just energy, scaled by a conversion factor. You are not made of matter that has energy. You are made of energy that appears as matter. Every atom in your body, every cell, every tissue. You are a standing wave of bound energy fields, and the mass you experience is the relativistic sum of energies, moving too fast and bound too tightly to escape. This is not philosophy. This is measurement. When physicists calculate the mass of a proton from first principles using quantum chromodynamics, they don't add up particle masses. They calculate field energies. They simulate the interactions. They integrate the energy density of the strong force field inside the proton, and they get 938 mega-electron volts per c squared. The right answer. Mass is not fundamental. Energy is fundamental. Mass is what energy looks like when it's bound. This flips everything. You thought energy was a property of massive objects. Objects have energy because they have mass and velocity, or mass and position in a field. No. Objects have mass because they have energy. The causation runs the other way. A proton at rest still has mass, 938 mega-electron volts per c squared, because it still has energy. The quarks are still moving. The gluons are still mediating. The strong force is still binding. All of that is energy. All of that contributes to mass. If you could somehow freeze the quarks, stop them from moving, stop the gluons from being exchanged, turn off the strong force, the proton would lose almost all its mass. It would weigh almost nothing. The 9.1 mega-electron volts from the Higgs-granted quark masses would remain. The rest, the 929 mega-electron volts, the 99%, would vanish. Because that mass was never substance. It was energy in motion, energy in interaction, energy in confinement. Your body weighs what it weighs because of the speed and strength of forces inside your atoms. Not because of stuff, because of motion. You are not a collection of things. You are a symphony of energies, each contributing to the total. And when those energies resist being accelerated, when you push and they push back, you call that resistance mass. Einstein knew this. Feynman knew this. The rest of the world still thinks mass is matter. It's not. It never was. Richard Feynman was asked more than once to explain why things have the mass they do. He couldn't. Not because he didn't understand the mechanisms. He understood the Higgs field before it was confirmed. He helped develop quantum electrodynamics, the most precisely tested theory in physics. He knew how mass arose from field interactions, but he didn't know why an electron has the mass it has. Why 0.511 mega-electron volts per c squared? Why not 0.3? Why not 1? Why not 0? No one knows. The Higgs mechanism explains how particles get mass. They couple to the Higgs field. The coupling strength determines the mass. But why does the electron couple with one particular strength, and the top quark with another, and the muon with yet another? Physics has no answer. The standard model of particle physics contains about 20 free parameters, numbers that have to be plugged in by hand because the theory doesn't predict them. They must be measured experimentally. The masses of the fundamental particles are among those parameters. You measure them. You write them down. You use them in calculations, and the calculations work beautifully. But the theory doesn't tell you why those numbers are what they are. An electron is 1/1836, the mass of a proton. Why that ratio? Why not 1 over 2,000? Why not 1 over 1,500? The up quark is lighter than the down quark. Why? I reverse their masses, and you get a completely different universe, one where atoms might not be stable, where chemistry might not exist, where you wouldn't be here to ask the question. But nothing in the laws of physics explains why the masses are tuned the way they are. Feynman found this deeply unsatisfying. He was honest about it, brutally honest. When a student asked him why particles have mass, he could explain the mechanism. But when pressed on why the mechanism produces those specific values, he admitted ignorance. He said, "I can't explain it. I can tell you how it works, but I can't tell you why." This is not a failure of physics. This is the edge of physics. Science describes how the universe behaves. It builds models, tests predictions, refines theories. It maps the territory with extraordinary precision, but it doesn't always tell you why the territory is shaped the way it is. Why does the Higgs field exist? Why does it have the specific field strength it has? Why do particles couple to it with the exact strengths they do? No one knows. Some physicists hope a deeper theory will explain it. String theory, for instance, promises to derive particle masses from fundamental geometry. But string theory is not confirmed. It may never be. Others suggest the anthropic principle. The masses are what they are because if they were different, we wouldn't exist to observe them. Universes with different mass values might exist, but we necessarily find ourselves in one where the values permit complex chemistry and life. That's not an explanation. That's an observation about selection bias. Still others accept that some things might be brute facts. The universe has certain parameters. They could have been different, but they aren't. That's it. Feynman leaned toward honesty over speculation. He refused to pretend he understood something he didn't. And he didn't understand why the electron has the mass it has. Neither does anyone else. You might find this disturbing. Physics is supposed to explain things. It's supposed to give answers. It does, but not to every question. Physics can tell you how mass arises from fields. It can calculate binding energies with stunning accuracy. It can predict the behavior of particles in accelerators, the dynamics of stars, the evolution of the universe. But it cannot tell you why the numbers are what they are. And Feynman wouldn't lie to you about that. He wouldn't dress up ignorance as insight. He wouldn't invoke mystery to cover gaps. He would say, "We don't know. We're working on it. Maybe we'll figure it out. Maybe we won't." That's honesty. That's science. And it means that even after explaining the Higgs field, even after describing binding energy and quantum chromodynamics, even after showing you that mass is not substance but interaction, there is still a final question that has no answer. Why does the universe resist acceleration the way it does? Why is mass the value it is? You can ask, but the universe doesn't answer. It just resists. You are not made of matter. You never were. You are made of fields. Quantum fields that permeate all of space, vibrating in specific patterns, localized into what you call particles. An electron is not a tiny ball. It's a ripple in the electron field. A quark is not a speck of stuff. It's an excitation in the quark field. A photon is not a particle of light. It's a disturbance in the electromagnetic field. Every particle in your body is a pattern, a wave, a standing oscillation in a field that extends across the universe. And your mass, the thing you've thought of your entire life as the measure of how much you exist, is just the resistance those field patterns have to being accelerated. Nothing more. You are not a collection of objects. You are a structure of interacting field disturbances, bound by forces, sustained by energy. The strong force holds quarks into protons. The electromagnetic force holds electrons to nuclei. The electron field and quark fields ripple in coordinated ways, creating the illusion of discrete particles. But there are no particles, not really. There are only fields. And you are a temporary, localized arrangement of those fields, one that resists changes in motion. That resistance is what you call your mass. When you stand on a scale, you are measuring how strongly the patterns of your fields couple to the Higgs field and how much binding energy holds your quarks together. When you feel the weight of your body, you are feeling the Earth's space-time curvature accelerating your field patterns downward, and those patterns resisting. You think of yourself as solid, as real, as made of something. You're not solid. You're mostly empty space with point-like excitations in fields. You're not made of something. You're made of patterns in nothing. And those patterns resist being accelerated, so you experience yourself as having mass. Feynman knew this. He spent his career teaching people to see particles not as things, but as interactions, as probabilities, as ripples. He knew that the deeper you look, the less substance you find. And he didn't try to comfort you about it. Because the truth is not comforting. The truth is that you are not what you think you are. You are not a thing moving through space. You are space, or rather fields in space, arranged into a pattern that thinks, a pattern that resists, a pattern that persists for a few decades before dispersing back into the fields from which it arose. Your mass is not proof that you exist as a solid entity. Your mass is proof that the universe resists changes to the pattern you currently are. And when that pattern dissolves, when the binding energy releases, when the fields decouple, when the oscillations cease, your mass will remain in the universe, not gone, not destroyed, redistributed. Because mass is energy, and energy is never lost. The fields that make you will still exist. They always existed. They always will. But the specific pattern that is you, the arrangement, the structure, the resistance you call your body, that pattern is temporary, and its mass was never yours to keep. It was only yours to resist with, for a while.